In this session, I will discuss about airfoil selection criteria. The airfoil selection is an important part of overall wing design. Selection of an airfoil for wing depends on flight requirements, whether the wing must be designed for subsonic, supersonic, or transonic flight design requirements. The designer must also consider other requirements such as airworthiness, structural, manufacturability, and cost requirements. Now we shall learn criteria to select an airfoil for wing with collection of designing requirements such as the airfoil with highest maximum lift coefficient, the airfoil with proper ideal or design lift coefficient, the airfoil with lowest minimum drag coefficient, the airfoil with highest lift to drag ratio, the airfoil with highest lift curve slope, the airfoil with lowest pitching movement coefficient, the airfoil with proper stall quality in the stall region. The airfoil should not be so thin that spars cannot be placed inside. The airfoil must be manufacturable. The cost and design requirements must be considered. For example, if the fuel tank is chosen to be placed inside the wing inboard section, the airfoil should provide sufficient space for this purpose. The table on the slide shows typical values of maximum thickness to chord ratio for various types of aircraft. For low-speed aircraft, the thickness to chord ratio between 15% to 18%. High-speed aircrafts have maximum thickness to chord ratio between 9% to 12%, whereas for supersonic aircrafts, it lies between 6% to 9%. Next, we have steps for wing airfoil selection. The first step is determining average aircraft weight in cruising flight, that is, W average equals half Wi plus Wf, where Wi is initial aircraft weight at the beginning cruise, Wf is final aircraft weight at the end of cruise. Next step is to calculate aircraft ideal cruise lift coefficient. As we know, in cruising flight, the aircraft weight will be equal to lift force. So, lift L equals weight W, which implies half rho V square SCL equals mg. Hence, ideal cruise lift coefficient CLC equals 2 W average divided by rho Vc square S, where Vc is aircraft cruise speed, rho is air density at cruising altitude, and S is wing planeform area. Next step is to calculate wing cruise lift coefficient. Basically, wing is alone responsible for generation of lift. The other components also contribute to total lift of about 20%. Therefore, the relation between aircraft cruise lift coefficient and wing cruise lift coefficient is a function of aircraft configuration. The contribution of fuselage, tail, and other components of the aircraft will estimate the wing contribution to the aircraft lift coefficient. At the preliminary design stage, and if geometry of other components are not yet been determined, this equation can be used to find the wing cruise lift coefficient, that is CLCW equals CLC divided by 0.95, where CLC is ideal cruise lift coefficient. Next, calculate wing airfoil ideal lift coefficient, that is CLI equals CLCW divided by 0.9, where CLCW is your wing cruise lift coefficient. Next, calculate aircraft maximum lift coefficient, that is CLmax equals 2 WTO divided by rho naught Vs square into S, where Vs is aircraft stall speed, rho is air density at cruising altitude, and WTO is aircraft maximum takeoff weight. Next, calculate wing maximum lift coefficient, that is CL max W equals CL max, that is aircraft maximum lift coefficient, divided by 0.95. Next, calculate wing airfoil gross maximum coefficient, that is CL max gross equals CL max W divided by 0.9, where CL max W is your wing maximum lift coefficient, where the wing airfoil gross maximum lift coefficient is airfoil maximum lift coefficient, where the effect of high lift devices is included. Next, select or design high lift device. Determine the high lift device contribution to the wing maximum lift coefficient, denoted by delta CL HLD. The table shows various high lift devices and their contribution to the wing maximum lift coefficient. In this table, the symbol CF by C denotes ratio between chord of high lift device to the chord of main wing body. Lastly, calculate wing airfoil net maximum lift coefficient, CL max equals CL max gross minus delta CL HLD, where CL max gross is wing airfoil gross maximum lift coefficient and delta CL HLD is lift coefficient increment by high lift device. Next, identify and select airfoil section that match the desired value of ideal lift coefficient CLI and maximum lift coefficient CL max. If the airfoil is designed for subsonic passenger aircraft, then select thin airfoil. The figure shows maximum lift coefficient CL max versus ideal lift coefficient CLI for several NACA airfoils. In this graph, the horizontal axis represents airfoil ideal lift coefficient and the vertical axis represents maximum lift coefficient. All the black dots represent one NACA airfoil section. If you found no airfoil section that matches desired ideal lift coefficient CLI and maximum lift coefficient CL max, then airfoil section that is nearest to the design point can be selected. This completes the steps for wing airfoil selection. With this, I will end up this session here. Thank you.